Welcome to my class. I'm Drew Collop. In today's class, we're going to discuss the standard curve. The standard curve is a graph that's used to quantitatively evaluate the concentration or amounts of different chemicals. We work with something called standards. That's why it's called a standard curve. A standard is the chemical of interest of known concentration. We take multiple standards, we measure them, and then we graph them. Once we have the graph, the concentrations of unknown chemicals can be determined by measuring the concentrations of known chemicals. For this, we're going to use a spectrophotometer. Let's look at an example. Here we're working with a chemical called BSA, bovine serum albumin. It is a very common protein found in the blood of cows, hence the bovine. Here we collected data to create a standard curve. We created a number of known concentrations of BSA. We then measured it on a spectrophotometer using an Amax of 550 nanometers. Please note that every chemical has a wavelength of maximal absorbance. For BSA, an absorption spectrum was done, and the wavelength of maximal absorbance was determined to be 550 nanometers. Hence, when we do the standard curve, we would like to use the Amax. The reason why that is because it will give you the biggest dynamic range of change. Notice, we placed in the concentration and we recorded the percent transmittance. Now, on our standard curve, we're going to compare concentration to absorbance. In order to switch from transmittance to absorbance, I need to use this formula right here. I plug in my percent transmittance, take the log of that, make it negative, subtract it away from 2, and then I will get absorbance. So we can do that calculation now. 100% transmittance, we plug that in, we get 0 absorbance. So this data set here, these are the absorbances for my standards. Over here, these are my standards. Again, these are standards because I made them up and I know the concentration. What I can do now is I can take some unknown samples. Here, 2 unknowns. I can measure the percent transmittance, and here I get 2 values for the percent transmittance. Let's fill that in on my table. We'll call this one A, we'll call this one B. We can plug those values into my absorbance formula. We plug in percent transmittance, we calculate absorbance. Here we get and now we can set up a standard curve and determine the concentration of these 2 unknowns. Now, which value is our independent variable and which value is our dependent variable? Well, our independent variable is the concentration. I've made up those solutions. I determined what those values will be. Units are going to be milligrams per mil. That means my dependent variable will be my absorbance. Depending on what I choose for my independent variable will determine what the absorbance is. And there are no units associated with absorbance. It's one of those unique variables. Now we had a concentration from 0 to 9. And we had an absorbance. We're going from 0. Maximal absorbance from our table was 0.52, we'll say, something like that. Let's make sure they all fit on there. How many boxes do I have? 2, 4, 6, 8, 10, 12, 14, 15. I have 15 boxes. And I need 9 units. We can use this as a conversion factor to maximize our scale. So here it says every box is 0.6. If we multiply that by 5, we will get 3. So every 5 boxes is 3 units. Starting at 0, 1, 2, 3, 4, 5. Every 5 boxes, 3 units. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. You can see I've maximized my scale. Let's do the same for absorbance. We have 2, 4, 6, 8, 10, 12, 14, 15 boxes. And we have how many units? We'll say 0.6. 0.6 units of absorbance. How much is one box equal to? .04 units. To get a whole number, again, I'm going to multiply by 5 because that'll give me 4 times 5 is 20. Well, 0.2. So every 5 boxes is 0.2 units. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. I've maximized my scale. Now we've put our scale on here. Let's plot the data. So initially we had 0% concentration and 0 absorbance at the origin. We then have a concentration of 1 and an absorbance of 0.06. So 1 is going to be right about here, 0.06, right about there. We'll then have 3 and 0.16. 0.1, right about there. Next, we have 5 and 0.284. 5 and 0.284, right about there. 7 and 0.409. Lastly, our last standard is 9 and 0.515. Right about there. Let's connect that with a straight line. Here we have a line of best fit. Now notice not all of the points touch the line. That's why we did a line of best fit. Several issues here. When you're collecting real data, you're not always going to have all the data points touch the line of best fit. Also, I drew this by hand. And because I maximized the scale, it was quite a challenge to plot those. We're going to go ahead with this anyways. So here's my standard curve. Let's give it a title. Concentration versus absorbance? No, thank you. How about standard curve for BSA at 550 nanometers? A much better title. Please, again, don't use your axes as your title. Concentration versus absorbance? I despise that title. It doesn't bring anything else to the table. A title of standard curve for BSA at 550 nanometers? This is a much better title. It tells me what it is. It's a standard curve. It tells me what the chemical is I'm assessing. It also tells me the wavelength of maximal absorbance. Again, as a rule of thumb, don't use versus ever in a title. And please don't have the title as graph of standard curve. I can see it's a graph. You don't need to tell me it's a graph. In fact, when we publish this, it wouldn't even be called a graph. We call it a figure. Let's now use the standard curve to find out what the concentration of my unknowns were. So what I did, I used a spectrophotometer to determine my unknowns. I had my unknown A. It had a absorbance of 0.228. 0.228. Right about there. This was A. And our unknown 2 was 0.346. 0.346. Right about there, we'll say. B. So I have the absorbance. What I now do is I use a ruler and I draw a horizontal line across from that arrow to my line of best fit. Notice I drew the line until it touches my line of best fit. Now I will draw a vertical line from the point where my horizontal line touches the line of best fit. I will start there and I will go down to my horizontal axis. Again, try and make a vertical line. Now we can read off where that hits this axis. Let's now try and determine exactly where that hits that line. Each unit is 0.6, so 3.6, that would be 4.2 would be on the line, so it's a bit shy of that. So we'll call it, we'll say 4.0. Best guess. Over here, we examine this one, it's 0.6. Bit further than that, so we'll call that 6.2. This would be in milligrams per mil. Milligrams per mil. So this is how you use a standard curve. You take a number of standards. These are concentrations that are known. We then use a spectrophotometer. We measure the transmittance. We calculate the absorbance. We can then plot that on our graph. Concentration as my horizontal independent variable and absorbance as my vertical dependent variable. When I plot that, I create a line of best fit. I will then use this line of best fit as my standard curve. I will have the absorbances for my unknowns. I will place those onto my vertical axis. I will draw a horizontal line across to my standard curve and then a vertical line where it reaches my horizontal axis. I will then try and read off to the best of my ability what that concentration is. Therefore, from my standard curve, A is equal to 4.0 milligrams per mil, and B is equal to 6.2 milligrams per mil. This is my best estimate based on my standard curve. Now I say this is my best estimate because you can see I graphed this by hand. To maximize my scale, it was difficult to plot exactly where those points should be. I did the best I could. However, there's a much better way to go about this. Let me show you. This is all about interpreting data. Being able to graph data and effectively determine what it represents is a critical skill to working in a laboratory. Much of the time you'll be working in our labs, you'll be writing graphs by hand, simply because we don't have a computer for everybody, and students bringing their own personal computer into the lab can be a challenge with contamination of both chemicals and biologicals. In the working world, all graphs will be done digitally. However, as educators, we believe graphing it by hand will allow you to build a stronger skill set for graphing data digitally. What I'm going to do now is I'm going to do the exact same data set, but now I'm going to do it in Excel. I'll walk you through all the steps. Let's try that now. We'll first open up a new worksheet in Excel and then input our data. We'll create a scattered plot using our concentration and our absorbance. We will move that chart to a new sheet so we have more space. We will create an appropriate title. We will add axes. We'll adjust the axes so that we're using the maximum amount of area on the graph. We will add a trend line. We will format the trend line. We will add a legend. And then finally, we'll use the equation we get from that graph to calculate our concentrations of unknowns. Let's show you step by step now. Switching over to Excel. So here's Excel. Let's type in our data. Standards were 0, 1, 3, 5, 7, 9. We had unknown A, we had unknown B. Let's center those. We got the percent transmittance from our spectrophotometer. We then measured the absorbances of our unknowns. And here's all the data we got from our spectrophotometer. Let's now start processing the data. We use the transmittance to calculate the absorbance. Notice I can use formulas here. I can say equals 2 minus the log. I put brackets in. I select the cell I want it to work with, and I hit enter. It goes to 0. Now notice I can take this formula here, and I can take the corner, I can drag and drop it down. What this is going to do, it's going to move this formula to all the other cells. What it'll also do is it'll move that B2 down to B3, B4, so on and so forth. So notice we have B2, then B3, then B4, and if you double click it, you can see it's highlighting where the calculation is coming from. So we've opened a new Excel file, we've input the data, and we've done some calculations. Let's now create our scatter plot. Now we're going to create a scatter plot of concentration versus absorbance. Now to create my standard curve, I'm going to highlight all of my concentration standards. I will hold down the control button, and I will highlight the associated absorbances. I'm not going to highlight my unknowns because I don't want them to be part of the scatter plot itself. I will click Insert over here. Scatter plot, I'm going to choose the one without the connected lines. And here is your graph right here. The graph is quite small. I can move it to its own sheet. So I will right click on the chart. I will select Move. I will click New Sheet. Right here. It has now moved it to its own sheet. Notice I have the graph now on its own sheet. Down here, you can see we have tabs. We can switch between the data and my graph. Let's now create an appropriate title. We could click on this, double click, and type our title. Let's call it Figure 1 dot Standard Curve for BSA at 550 nanometers. A much better title. Let's now add axes labels. Once I click on the graph, you'll see I have some new menu items that come up here. I can click Design. Over here, this is where we're going to access the majority of the functions we're going to use. So let's click on this, and we will click on Axes Titles, and we'll do the horizontal axis first. So now you can see a title at the bottom here. This was concentration, and my units are milligrams per milliliter. Hit enter, adds that title down below. Let's now go and add our title to our vertical axis. This was absorbance, no units. Notice the points and the values on the graph look very small. Let's try and adjust that now. We can click on that, home. Let's increase the font to 18. That looks better. Do the same on the bottom here. Click on it, home, and we will increase the font to 18. Same for our title here. It's quite small. Home, and increase the title. We'll put this one to 20 because it's a title slightly larger. Now that's looking a bit better. Now notice our units are quite small as well. Let's try and adjust those. Let's make those 14. And the same here. Much better. Notice my horizontal axis, it goes to 10, but I only really need it to go to 9. So let's adjust that. I'm going to right click on it. I'm going to click Format Axis. I can then adjust this down. My maximum will go down to 9. Hit enter and close that. And you can see now we're maximizing the area of the graph. Now notice my points are quite small. I'm going to right click on it, format data series. I will then go to the paint bucket. I will make sure you can switch between line and marker here. I'll make sure I'm on marker, and then I will go to width, and I will increase the size of those points. Let's go to 3. There we go. Now we can see it much better. Let's now add a line of best fit. Once again, I will click on one of the data points, right click. I will click Add Trend Line. This is your line of best fit. You can see there's many options here: linear, logarithmic, polynomic, moving average. We're just going to choose linear. I'm also going to scroll down here. Before I do that, notice it's added a straight line to this graph. If I click Display Equation on the chart, I get the equation for this line of best fit. Right here. Let's enlarge it. And now we have a linear equation for the line of best fit. Notice y equals mx plus b. We have a slope and we have a y-intercept. Oh, notice the chart has gone off a bit. Let's adjust that. We're not going to have negative absorbances, so we're going to change this to a 0. Much better. Let's now use this equation to solve for my unknowns. Switch to my sheet. So in this equation here, what is y? Y is my dependent variable. So y was equal to my absorbance. X in this situation is equal to concentration. Now I want to know concentration, meaning I want to solve for X. So let's rearrange this and solve for X. I'm going to swing my constant over to the other side. X is equal to Y plus, in this case, 0.1230. That takes care of that. I also now need to divide both sides by my slope there. So now I have an equation that's now solved for X. What I can do is I can take this, I can copy it, paste it down below. I'm going to remove the X part. I'm going to remove the spaces. And I will highlight the absorbance. This will then give me a calculated version of my concentration. Notice here, we have, let's round this off to 2 significant digits. Rounding this off, we have 4.0 milligrams per milliliter. And down here we have 6.0 milligrams per milliliter. From my digitally created standard curve, I determined my concentrations of unknowns to be 4 for A and 6 for B. What did we get from our handwritten curve? 4 for A and 6.2 for B. So pretty close, but not 100% perfect. To be honest with you, graphing using this program where it's capturing my images is quite difficult. If I did this on paper, I probably would have done a much better job. But using a computer program to create the data, to both graph it and determine what those concentrations will be, is how you'll work with this in the future. One thing to note, quite often you'll need to write a legend in here. Say I had different curves on here. I could do that by going back to Design, Add Chart, and Legend down below. Put it to the right. And you could change this up however way you would like. But as you can see, this is our standard curve. We create a number of standards. These are the chemical of interest of known concentration. We use a spectrophotometer to determine what the transmittance is, we then use our A equals 2 minus log percent transmittance to convert that to absorbance. We will then plot the absorbance as our vertical axis and our concentration as our horizontal axis. We will plot the values from the standards onto the graph. We will then use the absorbances from our unknowns, put those onto our vertical axis, draw a horizontal line until it reaches the standard curve, and then draw a vertical line until it reaches the horizontal axis. We will then read off from the horizontal axis what the concentration is. We can do this by hand, or we can do this digitally. I now have a practice question for you. Here is a different chemical called fluorescein. Its A max, its wavelength of maximal absorbance, is 475 nanometers. We have a number of standards here. Notice they're in molarity, and we have some unknowns, 2 of them. So I'd now like you to repeat what I did with this new data set. Do it by hand, graphing it, and then do it in Excel, digitally. See what the difference is. Which one do you think would be more accurate? So here is a table of values. Finish that off. Here is a graph to work with, and then open up Excel and graph that. So pause your video now, and then when you're done, unpause it and come back, and I will tell you the answer. I'm not going to write it all down. I will just tell you what the answer should be. If you've done this correctly, you should find one of the unknowns is quite difficult to determine using your handwritten standard curve. Why? It's very close to the origin. What you should get in the end is about 1.3 times 10 to the 6 and 1.3 times 10 to the 5, give or take. For a first-year math class, this would be considered advanced graphing. You will do much more of this in your laboratory courses and in your upper semester courses. If you're going to enter a laboratory career, you're going to be doing this quite a bit. So I wanted to get you a jump start on both graphing it by hand and graphing it in Excel. Remember, when making a graph and submitting it to the world, that is your final product. Nothing else matters. So I would advise you to take your time and make sure it looks very professional. You would not believe some of the graphs students have handed in. If it doesn't look professional, no one wants to read it. That's all for today. Until next time.